This dictionary defines gravity as the pull towards the center of the earth. And if we ask different people, that's probably the most common definition we would hear. Yes, many textbooks and dictionaries have given that as their definition. Too bad it's incomplete. It's silly to think that gravity is simply the pull towards the center of the earth. An astronaut on the moon would not go along with that. He or she would experience a pull towards the center of the moon. Actually, gravity is an attractive force that acts between any two objects. There is an attractive force between you and your books or you and your desk. The greater the mass of an object, the greater its gravitational attraction. Because the Earth is the most massive object close to us, its gravity has the greatest influence on us and on objects in our world. If we drop something, it falls towards the center of the Earth. The ground gets in the way and we have a mess. So on our planet it does appear that gravity is the pull towards the center of the Earth. But we must remember that all objects have gravity. The greater an object's mass, the more gravity will affect it. Mass and weight are not the same thing. Weight is the measure of the gravitational attraction of an object. On the moon, the gravitational attraction is much less than on Earth. The moon has less mass than the Earth and therefore has only 1/6 the gravity. That's why this lunar rover bounces around so easily on the surface of the moon. Astronauts on the moon would weigh less than they would on the Earth, and all their supplies and the lunar rover would weigh less. If this astronaut weighed 180 pounds or 82 kilograms on Earth, he or she would only weigh 30 pounds or 14 kilograms on the moon. He or she didn't shrink or change size. The pull of gravity is simply lower, so he or she weighs less. His or her mass remains the same. That's because mass is not the same as weight. Mass is not a measure of gravitational attraction. It is often defined as the amount of matter in an object. Scientists like to think of mass as the measure of an object's resistance to motion, either getting an object moving or slowing it down. The greater its mass, the harder it is to speed up or slow down the object. When we weigh ourselves, we use a spring scale. A spring inside the scale is stretched. It tells us how hard gravity is pulling down on us. Our weight is a measure of the gravitational pull on our body. To measure an object's mass, we use a balance scale and a set of weights. We can mass this fruit and then take it to the moon. The mass would be the same, because the change in gravitational attraction will have the same effect on the massing weights as the fruit. Weight and mass are not the same thing. For centuries, scientists struggled to explain why objects fall towards Earth. People could see that objects fell, but no one could explain how or why. It wasn't until the late 1500s that Galileo began to establish some ideas about falling objects. Here is a shot put and a softball. They are about the same size, but the shot put is much heavier than the softball. If someone lets go of the shot put and softball at the same time, and from the same height, which will hit the ground first? Here we are all set to release the shot put and the softball. Watch and listen. There. They hit at the same time. Even though the shot put was heavier, both objects fell at the same speed. It is said that Galileo conducted a similar experiment with two cannonballs of different weight. The story says he conducted the experiment from the Leaning Tower of Pisa. That part of the story is probably false, but it's fun to believe that one day Galileo climbed the circular stairs and stepped out on the bell tower balcony. This isn't the real Leaning Tower, but it will help us imagine what it was like when Galileo let the two cannonballs fall. We won't use cannonballs, as the shot put and softball will work fine. Now the shot put and softball are released. There you have it. Two objects of different weights landing at the same time. Galileo was right. Objects pick up speed at the same rate. Now, let's try something with these two pieces of paper. The papers are identical. We'll crumple this one up and then drop them at the same time from the same height. Which would you expect to land first? Well, the crumpled paper lands first. The other paper floats to the ground. That's because the uncrumpled sheet of paper is held up by the air around it. The crumpled paper can move more easily through the air. It has less surface area for the air to resist. So in this case, the two objects didn't fall at the same time. It seems to go against Galileo's discovery. Actually, Galileo realized that air can affect the way an object falls, so he said that objects pick up speed at the same rate regardless of weight when gravity is the only force acting on them. When objects fall through air, they may have different speeds. This is because the air resists the fall of objects, and those that are lightest with respect to their size will be most affected. Here is a book and a piece of paper. The book weighs much more than the sheet of paper, and when they are released, the book hits the ground first. But if we put the paper on top of the book so that air pressure under the book can't affect and resist the fall of the paper, the two objects fall together. Objects in a vacuum would fall at the same speed. A vacuum is a condition where there is no air or other gases present. Most of the universe is made up of the vacuum of space. One of the astronauts on the Apollo 15 mission to the moon performed an experiment to show that Galileo was correct. The moon has no air. It has no atmosphere. There are no gases around it, so it is in a vacuum. Watch the experiment. A hammer and a feather were released from the same height at the same time. As you can see, the two objects landed at the same time. It showed Galileo was right. When gravity is the only force acting on two objects, those objects, no matter what their weight or mass, will pick up speed or accelerate at the same rate and in the same way. In a vacuum without air to slow down and resist the objects, the feather and hammer land together. On Earth, we would not get the same results because of air resistance. On Earth, we can create a vacuum with the use of a vacuum pump. The air in this tube is removed. We will release a coin and a scrap of paper, and again they fall at the same speed. Now, if we take this hammer and drop it, will it turn and land with the heavy metal end first? Or will it turn and land with the handle first? Or will it simply fall in this position? Watch closely as the hammer is released. If you were thinking about Galileo's prediction, you would have guessed correctly that the hammer would fall as held. The heavier metal end has nothing to do with how the hammer will fall. If we flip the hammer, sometimes it will land metal side first, sometimes handle first, and sometimes flat. When objects fall towards Earth, they accelerate due to the force of gravity. They accelerate at the rate of 9.8 meters per second per second. This means that the object's velocity increases by 9.8 meters per second for every second that the object falls. After the first second of fall, the object has a velocity of 9.8 meters per second. After 2 seconds, the velocity is 19.6 meters per second. After 3 seconds, it will be 29.4 meters per second. This velocity will increase until the force of air resistance equals the downward force of gravity. As an object falls, the upward force of air resistance increases. When the upward force of air resistance equals the downward force of gravity, the object's acceleration stops, and it continues to fall at a constant velocity known as the object's terminal velocity. A human's terminal velocity is around 190 kilometers per hour, which is about 120 miles per hour. Once this velocity is reached, the person continues to fall at that constant velocity. These skydivers can adjust their acceleration and velocity by spreading their hands and legs out in such a way as to create a greater surface area for air resistance to affect. Slight movements can change a skydiver's velocity dramatically. When objects are falling, it appears that they are weightless. If we think of weight as the force an object exerts against the supporting floor, then you can see that an object that is falling seems weightless because there is no supporting floor. A scale falling with the object would register 0 because the scale is falling with the object. 0 g, or zero gravity, is what the members of orbiting spacecraft experience while falling around the Earth. Here are some examples. On Skylab, America's first science lab in space, astronauts could run on a track that went in a complete circle. They could do complete flips, twists, and spins. Here is a demonstration of strength as the barbells are lifted out of view. And here are push-ups as never seen before. Two-handed push-ups, two-person push-ups, three-person push-ups, one-handed push-ups, and finally, no-hand push-ups. In zero-G environments, there is no up or down. Shuttle crew members sleep in any direction. Notice that when people relax in zero-G, their arms rise. Eating in a weightless environment can be quite unusual. Most people put their pants on one leg at a time. The law of universal gravitation was first introduced by Sir Isaac Newton in the late 1600s. The story is told that he watched an apple fall from a tree and developed the idea of gravity. From that simple, everyday experience, Newton was able to figure out that the same force that made the apple fall kept the moon and planets in their orbits. He said the force of gravity depends on the mass of the objects and their distance from each other. It is called the universal law because it applies to all objects in the universe. People might argue that the apple falling and the moon's motion are unrelated. However, as Newton stated, the moon is also being pulled by the Earth's gravity and is actually falling around the planet. If the moon were not, it would go sailing off into space in a straight line. So gravity holds us on Earth and keeps the moon in an orbit around our planet. All the planets of our solar system are kept in orbit around the sun because of the sun's gravity. And many of these planets hold moons in orbit because of gravity. Gravity, then, is more than just the pull towards the center of the Earth. It is found throughout the universe and is common to all objects, large or small. All things have gravity. The strength of gravity is determined by the mass of an object. The greater the mass of an object, the stronger its gravitational attraction. Two objects are attracted to each other, and we speak of the force of gravity. The strength of that force is based on the mass of the objects and their distance from each other. We know the Earth and planets are round, but why? It's because of gravity. The Earth is round because it has attracted itself together as far as it can. There are no corners because every part is the same distance from the center of the Earth. This holds true for the Sun and other celestial bodies as well. The question of why gravity exists was explained by Albert Einstein in 1916. He said that a large mass warps or bends space, causing objects near this large mass to fall towards it. We can show that effect by having a ball approach this warped area. Notice how the ball orbits around and within the warped area. So, according to Einstein, the massive sun has warped space around it, causing the planets to fall into orbits. Likewise, warped space around the planets holds moons in orbit around those planets. Warped space and all gravity are an important part of our world and our universe. When a massive star collapses, it may form a black hole. A black hole may be 1 billion times more massive than our Sun, and therefore have a gravitational force that is so strong that nothing that enters a black hole can ever come out. That includes light. Since light doesn't escape from a black hole, the black hole can't be seen. Now it is time for the program quiz. Provide a short answer for each of the 5 questions. Question number 1. Gravity is often defined incorrectly in dictionaries and textbooks. How would you define gravity? Question number 2. The terms weight and mass are often used to mean the same thing. However, they are different. Give a definition for each term. Question number 3. On the moon, why would a feather and a hammer dropped at the same height and time land together? Question number 4. On Earth, why would a feather and hammer dropped at the same height and time land at different times? Question number 5. How does weightlessness affect astronauts living in space?